Hello everyone. Alright, so I'm going to use this video to go over the quiz from the other day. I'm going to try to do timestamps below if I can figure out how to do them. I'm sure it'll be relatively easy, but here we go. Going over number one. You toss a sad muffin into the air. It hits the ground, I guess. How does the distance compare to the displacement? And draw a picture and reference your answers. Okay. So I'm just going to draw a picture real quick. The muffin's going to go up in the air and come back down in this case, and that would be its total distance traveled. Distance is simply, yeah, total space traveled through. It's like your odometer. It measures, doesn't care which way you're going, just cares about overall what your final answer is. Displacement, on the other hand, let's go with a different color here, starts here, and that is displacement. A couple ways to look at this is the change in space from initial position to final position. So this is by definition the space between final and initial. This should really be drawn as an arrow. I have a lot of people still not drawing an arrow. They drew something like this, which is okay, but certainly better drawn as an arrow. Space between initial and final positions is correct. To help you understand this, how does it relate to displacement? Well, let's say theoretically we went up in the air. We started in the air about, I don't know, let's go 1 meter, and then let's say it was thrown in the air 2 meters. What you'll notice is the distance going up, it would travel 2 meters, and then down, it would travel a total of 3 meters, which of course, for distance, would mean that the distance is 5 meters. On the other hand, if we were talking about displacement, this would be positive and this would be negative, which means actually our displacement is negative 1 meter in that case, because that's the change in space. But again, your short answer are distance should be the total space traveled, and then displacement is space between position initial to final. There you go. Question number one. Question number two. You'll notice these amazing drawings that I've done so far for you. The monkey moves from negative 30 meters, all the way to negative 22 meters in 2 seconds. Label that displacement there. Okay. Give the following that can be accurately measured. Well, slated for us in the problem, this guy right here is the position initial. Oops, that should be negative 30, not negative 3. Position final is given to us, negative 22 meters. Displacement can be calculated. This is just final minus initial, or it went 8 meters in the positive direction, so this is positive 8. 2 seconds. What is 2 seconds? Well, if it's not given to us any other way, we can pretty much assume that this is the time interval. This is how long the total event took. But the problem doesn't tell us when time began or when it ended. We don't know. We have no idea if this started at 30 seconds or 90 seconds. All we know that is that it changed by 2. So if it did start at 30 here, it of course would go to 32 over here, or 90, 92, but we don't know either of those two. Next, do I know average velocity? Well, by definition, change in position over change in time. Since we know both of those, yeah, this is positive 8 meters, and that's positive 2 seconds. So the average velocity is 4 meters per second. But do we technically know how fast the monkey was moving here at the beginning? No, we don't. It could have been stopped. It could have already been moving. It could be slowing down. The problem does not tell us. We do not make any sort of assumption on the fact that it started from rest or didn't. By the same measure, we don't know what the final is. So since we don't know either of those two, pretty much automatically we don't know the next two, because the change in velocity is velocity final minus velocity initial. Since we don't know either one of them there, yeah, there's no way to know this one. And of course, acceleration is change in velocity over change in time. So since we don't know it, yeah, we don't know it. We don't know how fast he was moving at the beginning or the end. These numbers would still make sense to us if the monkey was walking at a steady pace across, or if he was going fast and then slowed down, or he could be going slow and then speed up. all of which are completely fine, and we have no idea. So that is the answer. We know VI, we know VF, we know delta X. Don't know it, don't know it. We know delta T, we know average velocity, we don't know VI, VF, delta V, or A. Next. All right, this problem can be solved in a couple ways. I'm going to show you the first one kind of in real time. The second one I already have done for you, so if you want to like pause it to look at it, because I don't think it belongs to everybody, but you should probably give it a look. So, car's initially traveling with a velocity of 35 meters per second. That alone probably tells us it's going to accelerate since it said initially, or did it say initially? I guess it didn't. It said it's traveling 35 meters per second. Well, the next word, accelerates, tells us that we're going to be dealing with five variables here, and not just 3. Accelerates at a maximum rate of negative 7 meters per second squared. Now that did technically say maximum rate, which could mean it could change, but in this class it doesn't, so we don't have to worry about it. Can the car stop before hitting a wall 292 feet away? Now I had a couple of people convert this to feet per second and this to feet per second squared. You can certainly do that. I'm not gonna. I don't think that easy. I already have meters per second ready. So I'm gonna go ahead and take this 292 feet and convert with that conversion over on the left there. If you don't already have this conversion down, I would suggest it. But after calculating it, that's 89.02 meters. That's how far it is away. Now, what do we do with that 89.2 meters? Okay, this is where ease of doing this problem comes in. When you're asking a question, can something happen? Okay, there's 2 ways that you could plug this in. The first thing that you could do is I can put in 0 meters per second and say, all right, I've got these 3 numbers, and I'm asking math, all right, based on those 3 numbers, what displacement will definitely go with those? That is certainly the easiest way come on, I didn't do that. There we go, okay. With that, I would do this guy right here. Certainly the easiest way to solve this problem. Okay, velocity final is 0. I have 2 terms left. This left one should be subtracted on both sides. And then to get delta x isolated, I'm going to divide 2a on both sides. So note that I've got my given, find equation, algebra, and now I'm going to plug in. Negative, this negative is not canceled because it's not inside the VI squared divided by 2 times, it's a good thing it doesn't cancel because it better cancel with that one right there. And if I've calculated this correctly, I've got my answer key here somewhere. Where did my answer key go? Oh, darn, it's over here. Right back. This will make it go faster in the future, I promise. 87.5 meters. All right, now I should write this out, but for sake of time, I'm just going to say it. Here's what your answer should read. Okay, you've got these calculations on the page. The answer should read, no, it's not going to run into the wall because it's only going to travel 87.5 meters, and you should definitely compare that to, and the wall is 89.02 meters away, so it's saved by a total of about 1.52 meters. You don't have to say that last part, but you should definitely compare the first ones. So no, it should not hit the wall. Now, it shouldn't hit the wall no matter how we do this problem. So let's talk about the other thing that you could have done, which some people will see me mark on their page. The other thing that you could have done, since you technically don't know whether it stops or not, is you definitely could put this guy here, okay? I'm going to put that back in a second because I have this work on the next page, and I will have this work also posted for you to look at as well. But do I know it's going to go 89.02 meters? No. Let's look at the next page here. So here I have it set up, and same sort of thing. I've got the same initial velocity. I've got the same final. But here I plugged in my displacement as 89.02 meters. I don't know that's going to happen. So I'm looking for velocity final. Same equation as before. We're just solving velocity final, and you'll notice me plugging the numbers in. And when you plug the numbers in, you get a negative underneath the square root, which can't happen. So this always messes with people. This would be an imaginary number, Spainhour. Or what does this mean? What it means is, if that is your initial velocity, let me highlight a little bit better here. If that's your initial velocity and that's your acceleration, then this can't happen. Of course, we know that because we look at the last page. Look at the last page. Oops, wrong button. Look at the last page. And we see, yeah, with that initial velocity and that final and that acceleration, the max displacement it's going to go is 87.5, which means it definitely cannot go 89.02. So what does this imaginary mean? This can't happen, and once again does not make contact with the wall. Contact, no contact with the wall, because that can't happen. If it were to happen, this would actually end as a positive number, meaning you're traveling at some speed when you hit the wall. So yeah, you do make contact with the wall in that case. Let's move on to number 4. All right, dead unladen swallow. For those of you uneducated, not seen Monty Python, it's a bird. It's a dead bird, people. All right. Is tossed up into the air and measured with an average airspeed, velocity, blah, blah, blah. It's a joke from Monty Python. Apparently, some of you don't get that. It's cool. It's whatever. I'm not going to worry about it. It doesn't bother me in the slightest. So initial velocity here should be 7.2 meters per second. Acceleration, since it's in the air, by the way, 0 up is positive. Sorry, let's go back. 0. You got it. All right. And finishing this guy off, displacement, VF, and delta T. All right, so the first question that is asked is how high does it go? This displacement is what we're trying to find. We know that at the top it will be 0 meters per second. These variables are on the way up. So I am looking in this particular set of variables for an initial position, of course, right here, and the final is right there. So I am measuring everything there. Now, as I draw that picture, what you might note is that that arrow is not the total height. The problem specifically tells us that it was thrown from a height of 2.1 meters. I do not have, come on, why are you not putting the dot there? That hurts. So that's going to be 2.1 meters. Hold on, let's fix this. It's going to bother me. 2.1 meters. Okay, move over here. 2.1 meters. Done. That's weird. All right. So that does not belong in this initial set of variables. Now, to find this set of variables, I actually use very similar math to what I did on the last problem. And this cancels, subtract that on both sides, divide by 2a, and you end up with delta x, which is equal to negative 7.2 meters per second. The whole thing is squared times 2, negative g, there we are, which is good because the negatives cancel like they should since the negative's on that side, and you end up with 2.64 meters. Now that's not how high it goes, because if it asks how high, that would be relative to the ground. So to get how high it goes, this is just the, here, let's use a different variable for, that's how much height has changed. So to get the final, we would take the initial plus the height change to get the height final, aka we need to know this height, that's the initial, plus how much it changes in order to get the final. So that just means 2.1 meters plus 2.64 meters is a total of 4.74 meters. That's your answer to A. For part B, there's a couple ways you can do it. Why are you not listening to me? Come on, here we go. The first way is this. I already know stuff on the way up already. So I'm just going to go ahead and do a little bit of math right now and find out this time. Now that time is not the total time before it hits the ground. That is just the way up, but I could still use this. We have what? A equals VF minus VI over delta T. So why do you keep doing that? That's irritating. Delta T is equal to VF minus VI over delta T. VF, oops, sorry, over over A. VF is 0, so this should be negative 7.2 meters per second over negative g for a total time of, right here, 0.73 seconds. Okay, then what you're going to have to do, because that's not the total time, is you're going to have to worry about what about when it's going down. And velocity initial of going down, 0 meters per second, because we are going now from down. So that is my new initial. That's my new final. I don't know how fast it hits the ground. I still know that acceleration is negative g. There's the time I'm looking for. And because of solving on the previous problem, I know that the total displacement is negative 4.74. Why not just negative 2.64? Because it's going to go all the way to the ground, that total. So, and I can go find this guy. Now, to get that time, I'm going to use this equation. Some of you are afraid of this equation now because we've been using quadratic with it a couple times, but you will notice you don't have to worry because that cancels, which means we just have some nice algebra. Move both easy algebra. Multiply 2 on both sides, divide a on both sides, square root. That'll get you delta t. 2 times negative 4.7 meters divided by negative g. Look how those negatives nicely cancel. Put that all in and you get 0.98 seconds. If you want an equation for the very end, let's go actually over here. Let's say that the time up plus the time down is equal to time total. So 0.73 seconds plus 0.98 seconds ends up at 1.71 seconds, the answer to this problem. Now, the reason you can do it like this is because we split up the set of variables. You can also do the time. You definitely have to do the height this way right here, because there's no other way. But the time you could also have done in a different way, and that is simply this. Instead of splitting it up, since acceleration is the same the entire time, we could set that that is the initial position and that's the final. And I'm just going to flip forward. I've already done this problem, so if you need to kind of look it over, definitely hit pause on this next part. But yeah, so we set the initial as 7.2 because that was it here. We still have negative g, but the displacement is negative 2.1 because it's going from here down there, just like in problem number 1. Now, what I've done over here is I've done the math on the left side. That work is done here, okay? And you plug numbers in. Biggest mistake made, when I make displacement go on the right side over here, I make it negative here, and the displacement is also negative, so those will cancel, giving me a positive c term right there. If you do this correctly, you'll get 2 answers, the right one and a negative one. Obviously, the negative one is wrong. We can talk more about that one a little bit later. Finally, let's do number 5 just real quick, because you just heard the bell, and I've got a class to teach the next hour. Will is running at max speed. Because that's max speed, this is just a constant velocity problem. So the displacement he's going to go is 7 meters. Time is 3 seconds. And finding that is simple. Velocity is displacement over time, or 7 meters over 3 seconds, or 2.33 meters per second. Now, he ran that 7 meters, but then he runs into the elephants behind. Since this is a different acceleration, of course this one being 0 and this one being something else, this requires a whole new set of variables. Since he's accelerating, I'll put these up right here. And the velocity initial is, of course, 2.33 meters per second, because that's what he ended. We're trying to figure out how much time it takes him to stop. So there's 0. And it tells us that's 10 centimeters. So converting 10 centimeters to meters, that should be 0.1 meters. Now, you can do this in 2 ways. We want to get time. I'm just going to go straight to it. The other thing you could do is you could go get acceleration, which is fine if you want to. It's negative 27 and change, but it's definitely going to be easier for me to just go get this one. So to do that, I'm going to plug this equation in here. I'm going to cancel what cancels, which is VF. I'm going to multiply 2 on both sides. I'm going to divide VI, because it's the only thing multiplying over there. That gives me delta T. 2 times 0.1 meter over 2.33 meters per second gives me 0.086 seconds. I had a bunch of people answer 0.09 seconds. You should definitely, let's just make this general rule, you should probably at least have 2 significant figures. 1 significant figure is probably not specific. All right, thank you very much. There's the quiz.